Hi and Assalamualaikum to our laboratory instructor Dr Aizuddin Supee. Today, we are Group 2 would like to present our lab report which is single-stage compressor. First of all, let me introduce our team. Our group consists of 4 members which are Afina Aina, Ahmad Luman Akil, Fakhrul Rashid and me, Muhammad Hanis. What is single-stage compressor? Based on my knowledge, compressors are mechanical devices used to increase the pressure of various gas or fluid that can be compressed. A single-stage air compressor is powered by a pressure-sensitive valve and the force of a piston. With each piston stroke, the single cylinder within is designed to compress air. This cylinder is connected to a power source that provides the force needed to compress the air. It is different from the air compressor with two or more stages because it only has one cylinder and one valve. In this experiment, we also will measure the rate of compressor heating up and the rate of heat loss from the compressor. Let's take a look on the objective of the experiment. Objective 1 is to illustrate first law of thermodynamics about energy conversion. Then objective 2 is to see the conversion of mechanical work into heat energy. Let's move into the next slide. What is the theory used in this experiment? Firstly, the working principle of single-stage compressor. In a common single-stage vane compressor, a constant volume of air is confined between two sliding vanes powered by an offset rotor. This volume of air is subsequently forced through the outlet, where the area and hence volume are reduced. As a result, its pressure increases and it is forced out of the outlet port. Other than that, the conversion of work into heat energy. Step 1. Work input. The motor does work on the piston to compress the air. This work is the energy input to the system. Then compression. As the air is compressed, its pressure and temperature increase. This is due to the work done on the air molecule which increase their kinetic energy. Lastly, heat generation. The increase in temperature of the compressed air is a direct result of the work done on it. This heat is generated because of the energy input partially converted into thermal energy. Apart from that, there are some laws related in this experiment. Law number 1 is first law of thermodynamics. This law states that energy cannot be created or destroyed, only transferred from one form to another. In the context of the compressor, the mechanical work done is converted into heat energy within the compressed air. Next is the ideal gas law, which is PV equal to nRT. When the air is compressed, the pressure of air increases, causing that the volume decrease and the temperature increase. Then, adiabatic compression. The compression process is adiabatic, means that no heat is transferred to or from the surrounding. The work done on the air increases its internal energy and raising its temperature. Aside from that, we have calculated the energy added to air by compressor and the heat emitted from the compressor. To perform the calculation needed, there are several equations to solve the problem as shown in the figure 2.
Assalamualaikum and good day to Dr Aizuddin and everyone. My name is Nur Afin Aina binti Ahmad Razani and I will proceed the presentation with the experimental setup. So for the apparatus, the first one we have the airflow meter, where the atmospheric air will flow into it. The second one is the inlet valve, where we can adjust the valve to control the airflow. Next is the air chamber 1. Also, we have the motor and power switch box, where we can turn on and off the power. Next, we have the spring balance, and also compressor, which powered by the motor. And we have the second air chamber and the outlet valve. Okay, so for the instrument, we have the barometer to measure the atmospheric pressure, and also the tachometer to measure the power of the motor.
This is the procedure of the experiment. First, the power was switched on. Second, the green valve was fully opened by turning it anti-clockwise. Next, initial reading for all parameters needed was recorded. The reading of motor speed was recorded by using tachometer. Fourth, the motor was switched on. Then, the red outlet valve was turned to set outlet pressure P2 to 1 bar gauge. Sixth, the spring balance of the motor was adjusted. Lastly, the temperature of outlet air T2 was recorded at 1 minute intervals until two consecutive readings are the same. To stop the experiment, first, compressor outlet pressure P2 was reduced to 0 bar gauge by using red outlet valve. Last but not least, the motor and the power was switched off.
Hi and Assalamualaikum. My name is Ahmad Lukman Akil bin Muhammad Yusari. I will discuss about safety procedures. First of all, you have to wear appropriate clothes with a long pant. Also, you have to wear a lab coat and a closed shoes before entering the laboratory. This experiment can generate heat, so you must wear a hand glove to open or close the valve after the experiment.
Next, we have the raw data and analysis. So the given data are length of torque arm L 0.2, compressor swept volume VCOM 267, specific heat capacity of air CP 1005. As mentioned in the methodology, we will have to record all the initial readings for these parameters in the table 1. And these data we abstract out to calculate the specific volume by using the formula of VO equals to V naught equals to RT naught divided by P naught, and we will get 0.858875 meter cube per kg. Second one, we will have to calculate the volumetric flow rate, which is the formula is V in divided by the 60,000, and we will get 4.5 times 10 to the power of negative 3 meter cube per second. The next one, we calculated the mass flow rate, which is volumetric flow rate divided by the specific volume, and the mass flow rate is 5.2941 times 10 to the power of negative 3 kg per second. And last one, we calculate the power of the motor, which is motor speed times motor spring balance times length of torque arm times 2 pi times 9.81 divided by 60, and we'll get 752.785 watt. Next one is the result. We have the table 2 outlet temperature data. From this table, we calculated the energy added to air by compressor HC and also heat emitted from compressor QC. Okay, so to calculate the HC, we use the formula HC equals to the mass flow rate times specific heat capacity times T2 minus T1. So from the example given, I have my T2 at 66 and insert all the values in the formula. We'll get HC equals to 191.541 watt. For the QC, calculated using the formula QC equals to the power of the motor minus HC and equals to 561.244 watt.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Thank you, Afina, for showing us the data that we get from the experiment from the single-stage compressor. Okay, first of all, I want to talk about the discussion, the graph part of our experiment. Okay, so how do we determine the x-axis and y-axis of the graph? Okay, it is simple only because in many experiments there are two variables, which is the independent variable and also a dependent variable. As you can see from the title itself, graph of temperature T2 against time T. The temperature is on the y-axis. So we know that the temperature is the dependent variable and the time is the dependent variable. Okay, so the temperature increased exponentially with time, but why? Okay, so in the single stage compressor experiment, as we know, there are uh, there are heat generated when the experiment are conducted. When the heat is generated, it will generate a lot of heat. When a lot of heat is generated, uh, the temperature will also increases. Not only temperature but also the pressure. Thank you. Okay, so we will move on to the second graph. The second graph shows energy added to air by compressor Hc against time. And we know that the energy added to air compressor Hc increase exponentially with time. Okay, first of all, we know that we have one dependent variable and also we have three independent variables. So we know that this graph, the y-axis would be the energy added to air by compressor and the x-axis would be the time. Okay, so we move on. We know that, as mentioned just now, when compressor work, the temperature will increase. When temperature increase, the pressure also increase. This the rise in temperature causes the air density to change, which can affect the flow characteristic and the efficiency of the compressor. The second one will be there are work done on the air. As we know, the work done on the air by compressor is related to the pressure differential and the volume of air being compressed. When this happens, the work required to compress the air increases, so the energy there will be more energy used when the compressor works. Okay, we will move on to the last part of the graph. The figure 11.3 shows graph of heat emitted from compressor QC against time. It is different from the two graphs that I have shown just now. It is because the heat emitted from compressor QC decreased exponentially with time. But why? First of all, when the compressor starts operating, it generates a significant amount of heat due to compression, work, and also the friction. So the initial surge results in higher temperature and heat emission. Okay, the second of all would be as the compressor run, the heat dissipates into the surrounding area. When we do the experiment, the surrounding area was very cold because it was raining that day. So the rate of heat transfer to the surrounding can decrease over time as the temperature difference between compressor and the surrounding decreases, leading to a reduction in heat emitted. And last but not least, we know that the experiment, the last part, uh, from our experiment, the temperature stopped at 153 degrees Celsius at 29 minutes. So it has achieved thermal equilibrium at 153 degrees Celsius at 29 minutes. So over time, the system tends to reach thermal equilibrium where the heat generated by the compressor balances with the heat lost to the environment. As the temperature stabilizes, the rate of heat emission will diminish, often following a exponential decay pattern. So it will decrease exponentially with time. Okay, so that's all from me. Thank you.
Now we're moving to the part of discussion. The question is, what will happen to the energy that is being input to the system when the system is heat up? First, increase in internal energy. Heat can is energy, so the energy added to a system increases its internal energy, causing particles to move or vibrate faster due to an increase in kinetic energy. Second, because of the particle vibrate faster, the temperature in the system will rise. Third, work. Energy can be utilized for work in expanding systems such as gases when the system expands against external pressure affecting the surrounding. Fourth, heat lost to surrounding. Some energy could be transferred to the surrounding in the form of heat. So not all the heat, not all the energy can be transferred to work. So the last question, the amount of energy lost as heat as compared to the work input to the compressor. And in the experiment, we can conclude that the amount of energy lost as heat is lower compared to the work input to the compressor. The second one, the amount of energy lost as heat as compared to the heat added to the air. In this experiment, the amount of energy lost as heat is higher compared to the heat added to the air until the minute of 5. But after that, at the minute of 6, the amount of energy lost as heat is lower compared to the heat added to the air until the end of experiment. Now we at the end of the slide. In conclusion, in this experiment, we can conclude that at outlet air temperature, which is T2, increase exponentially over time because of friction and gas compression. As the compressor heats up, more power is needed. Heat being generated reduce the mechanical and thermodynamic efficiency, leading to potential decrease in volumetric efficiency and output pressure. Over time, the compressor reached a steady state operating temperature where heat dissipation balanced heat generation. In this experiment, we can see at the last 2 minutes the temperature will not changing. So we can conclude that experiment there. However, the compressed gas remains at a higher temperature due to the compression process. If the compressor outlet pressure, which is P2, being reduced, the heat being generated and the work to be done will be less. That's all from us. Thank you.
Here are some of the references for our experiment. I think that's all from us and thank you so much for watching.